Okay, in the past couple of lectures, we've been talking about rates and rate laws. And in those rate laws, the rate constants were always just invoked as adjustable parameters, phenomenological constants. We talked also about diffusion, but it was only in connection with macroscopic length scales and transport effects. In this lecture, we're going to start talking about deriving rate constants from molecular principles, and we're going to see that diffusion, even at the molecular scale, can impose an effective speed limit for reactants in liquids. This is a theory that goes all the way back to 1917. It's a really beautiful piece of work by Smoluchowski. So we're going to think about hard spheres of two different kinds, A and B. They react on contact with each other. The radii of radius RA and particles of radius RB. So we're going to compute the rate under these rescue and replace conditions. They are basically the conditions of a steady state reactor. So it seems like an artificial construct, but actually if you really think about it, it's quite realistic. If you have, for example, a CSDR, constantly feeding your reactants in and then mixing them thoroughly, then the concentration of B in the bulk will be a constant, and the concentration right at the horizon where these things will react on contact has to be 0. And it should also be noted, of course, that this isn't really a concentration. We're talking about the molecular scale. Concentration at that scale is a little bit nonsensical. But what we can talk about is a steady state radial distribution function, and that's really the thing that we're working with. At infinity, away from the sink particle, the A particle in the sea of B's, then that radial distribution function goes to the bulk, steady state, and right at the surface it goes to 0, and in between, that's what we're going to work out. The concentration of B is going to be the notation that we're going to use for the bulk concentration. We also have a C sub B, which is going to stand for the concentration of B as a function of distance. Now at steady state, flux of B molecules to our target A molecule, we're going to treat this A molecule as though it's sitting there stationary for the time being. Since this is a sink and it's operating at steady state, then at any distance away from the A molecule that I draw a spherical dividing surface, there's a constant flux through that surface. And so that allows us to write down that NB is a constant. This is my flux multiplied by the cross-sectional area. And that should be equal to 4 pi r squared times, by Fick's law, the diffusivity of the B molecules times the concentration gradient of the B molecules with respect to R. And this is true for any value of R that's greater than that radius at which particles within that distance just instantly react. Now what we're going to do is we're going to integrate this differential equation. We're going to integrate that from the boundary condition at Ra plus Rb, where the concentration of B is equal to 0. We're going to integrate up to an arbitrary value of R, where we have some unknown function of R that tells us the concentration. Cb and R dependencies here are both separable. So that allows us to do just a basic integral. The concentration as a function of R now has this constant. This is the flux multiplied by the cross-sectional area divided by 4 pi times the diffusivity. And this little ratio pops out. This is 1 over Ra plus Rb minus 1 over R. Okay, so the other boundary condition that we need in order to finish everything off is that the concentration at R equals infinity should just go to that bulk concentration. So we plug that in, we solve for NB, and we get this equation. The rate of B consumption per A molecule is 4 pi dB times Ra plus Rb multiplied by the concentration of the B molecules. Now, if I want to convert that into the rate of reaction per unit volume of the liquid, I have to know how many of my sinks there are per volume of the liquid, right? So my sinks are these A molecules. And so that gives me a reaction rate. That's 4 pi d times Ra plus Rb times the concentration of A times the concentration of B. And you recognize that this is basically a second order reaction rate law. There's one last thing to patch up here, and that's that we did this calculation for stationary A molecules. So how do we account for the fact that both the A molecules and the B molecules are both diffusing around? Well, they're both doing random walks, and so we have two random variables, the position of A and the position of B, and we know from basic statistics that if you take a linear combination of random variables and you ask about its variance, that ends up being the sum of the variances of the two independent variables. So the effect of that is that our linear combination here, this allows us then to write the effective diffusivity for the distance between A and B molecules. The effective diffusion constant is dA plus dB. So Stokes-Einstein tells us that we can write the diffusivity of species A, kT, over 6 pi times the viscosity times the radius of the molecule A. You know, it's pretty amazing that we're going to be able to get a decent answer at the molecular scale by using this thing that you might think is only valid at the colloidal scale. But actually it works decently well, even all the way down to sub-nanometer sizes. So now if both A and B are mobile, then that tells us that we can write that diffusivity as this dA plus dB, replace each one of these by the corresponding Stokes-Einstein expression, and you get this expression for the rate. So you get 4 pi kT over 6 pi times the viscosity times 1 over Ra plus 1 over Rb multiplied by Ra plus Rb, and there's the A and B concentration factors. So now we're going to simplify this and recognize that that thing over the orange bracket here is actually just a second order rate constant. So the diffusion controlled rate constant now is given by, divided by, two factors of the radius down here, Ra and Rb. Now, when Ra and Rb are about the same size, regardless of their absolute sizes, this could be particles as small as a single small molecule and all the way up to the size of something like colloidal particle, then you have that the diffusion controlled rate constant is just this famous result by Smoluchowski, 8 kT over 3 times the viscosity. Now, how big is that number? Well, in water at 25 degrees C, viscosity, and plug in the temperature, we find that the diffusion controlled rate constant is 7 times 10 to the 9 liters per mole per second. So you should remember this figure. It's approximately 10 to the 10 liters per moles per second. And that's sort of one of the hallmarks of a diffusion-controlled reaction, is that it's becoming quite fast in terms of its rate constant. Now, the rate itself can still be quite slow if the A and B concentrations are both slow, because the rate, of course, is going to be the rate constant multiplied by those. It's also important to keep in mind that the viscosity can have some temperature dependence, but usually that's not, just to give you an overall temperature dependence in the diffusion-controlled rate constant of about T to the 1.75. So this is a weak temperature dependence compared to, for example, an Arrhenius law, and that's another one of the signatures of a diffusion-controlled rate process. Fast forward all the way to 1942, Debye generalized this to go beyond the hard sphere result of Smoluchowski. And the basic idea is that the long-range electrostatic forces between molecules, particularly when you're dealing with ions, can influence the frequency at which the ions can encounter each other. And the way that you can incorporate that effect is by just going back to the expression for the flux integrated over the entire surface and say that that's actually influenced now not only by the diffusion in the concentration gradient, but also with the explicit chemical forces. Okay, so now you have this derivative of the dimensionless potential amine force between particles. And this is now going to be valid for all r greater than some radius at which the particles react. So this time the equation is not separable. We're going to introduce this change of variables. We normalize the concentration as a function of r by the bulk concentration, and we equate that to something that represents a deviation from equilibrium, right? So if everything was at equilibrium, we would get that the concentration is just this potential amine force factor, Boltzmann factor, and we just multiply it by a xi of r function to account for how different the steady state radial distribution function is from the one that we would expect if everything was at equilibrium. And the result of this is that we get the deviation from equilibrium is given by this function over here on the right. Now we're going to integrate this, and that integration turns out again to be separable. Deviation at infinity minus the deviation right at the surface where they're instantly reacting is given by this ratio of constants. So I've got the flux divided by the bulk concentration divided by 4 pi times d times this lambda. Now lambda is a capture radius. So it's sitting right here where the r was, the radius theory of Smoluchowski. In this case, the capture radius is given by an integral from r star up to infinity of 1 over r squared e to the positive beta u dr. So this is lambda to the minus 1. And now let's go through and make sure that we keep our boundary conditions all straight here. So when we're at the reactive surface, then the concentration at r has to go to 0, where e to the beta u star is the value of u when I plug in r star. Then we have this deviation from equilibrium. Now that's never 0. The product of this and this has to also go to 0. We can do the same kind of analysis over here. The concentration in the bulk has to go to the bulk B concentration as I go to infinity. I know my Boltzmann factor with my potential amine force. That has to go to 0. E to the 0 is going to be 1, and that says that xi is just going to be the bulk concentration divided by the bulk concentration out at infinity, which just gives me a ratio of 1. Okay, so this is really what's going on over here. You see this little picture I've drawn. The black line represents the potential amine force. The orange line represents this upside down Boltzmann factor, e to the plus beta u of r changed from Cb over bulk concentration is this deviation from equilibrium times e to the beta. Okay, so now we're going to plug in these two boundary conditions. This one goes to 1, this one goes to 0, and now we can go back then and solve for total rate of consumption of B per molecule of A again. So this is the same arguments that we walked through in the Smoluchowski derivation, and this is the rate of consumption of B per molecule A is just given by 4 pi d times the capture radius times the concentration of B. Again, in order to convert this into a rate, we have to multiply by the concentration of A, and then we will again recognize that what we have is a second order rate law, and the second order rate constant then is 4 pi times d times the capture radius. So we're going to do all the same things. We're going to use the fact that these are both independently diffusing, and this d represents now the sum of the A and the B diffusivities. So let's go ahead and plug in some numbers and see what this particular theory predicts. Okay, so if we have a Coulomb interaction between two ions, then I've got the charge of ion A, the charge of ion B, divide that by the distance, but I'm going to write the distance in terms of Bejerrum lengths, and the effect of that is that I automatically convert my Coulomb potential into a Coulomb potential per unit of kT, and the Bejerrum length is just a unit charge squared over 4 pi permittivity times dielectric times kT, all of this in the denominator. So this by definition is the distance at which two charges in a dielectric medium epsilon can be brought together with a 1 kT difference in the energy. So in water, at 300 degrees Kelvin, with the dielectric constant of 80, Bejerrum length of 7 angstroms, and now I can integrate that expression for the capture radius, and I find that the capture radius relative to the reaction zone is beta u divided by e to the beta u minus 1. Beta u star, of course, is the Coulomb potential evaluated right at the point where these things are going to react upon contact. Now, what you really have here in the Debye theory is just lambda divided by r star times the original Smoluchowski result. So this lambda is basically something that accounts entirely within itself for the deviation from the Smoluchowski hard sphere result. So when you have ions that are attractive to each other, then the beta u star will be a negative number, and the Debye theory will be faster by some factor than the Smoluchowski theory. That factor of acceleration is the lambda over r star. Now the Smoluchowski case is the special situation where the particles interact like hard spheres, no interaction until they actually react with each other. And so there the beta u star is just equal to 0. At this point here, and recognize that that's actually just the Smoluchowski result, where the lambda over r star is equal to 1. As these things become repulsive, so if I have, for example, an electron transfer reaction between two cations, then it's going to be hard to bring these two cations close enough together, and that effectively reduces the rate relative to the Smoluchowski prediction. Okay, the last thing I want to work in here is partial diffusion control. So in many cases you have a reaction that's near the diffusion controlled limit, but the actual barrier might start to be appreciable, and we can mix the diffusion control and reaction barrier controlled rates together in the usual way. You can't react until you can get sufficiently close to do so. And so these two resistances just add like resistances in series to give you the overall rate constant for the reaction. We take 1 over k is equal to 1 over the diffusion controlled rate plus 1 over the reaction barrier controlled rate. So this, for example, might be a transition state theory rate constant. And obviously in this expression, whichever resistance is the largest is going to dominate this, and that's the one that's going to end up becoming the rate constant. An interesting question here is what size of an activation barrier leads to a transition state theory rate constant that ends up being the same as Kd? Well, if we just use Smoluchowski's Kd, we can begin to answer that question. So let's put the transition state theory rate constant over here. We've got a second order rate constant, so we have to have molarity to the minus 1, Kt over h prefactor, e to the minus beta delta g. We want to figure out how big that's going to be. And on the right, we have 8 kBt over 3 times the viscosity. In water at 25 degrees C, that gives me beta delta G star is minus the log of 1 molar times 8 Planck's constant over 3 times the viscosity. Kind of surprising here, this is 4 kcals per mole, and if you think about room temperature chemistry, then you're talking about something that's about 7 kT as a barrier. I think a lot of people doing biomolecular simulations might think about association processes where they have 7 kT barriers on free energy diagrams, and those processes might actually still be just diffusion controlled, even though this seems like it's an appreciable barrier and probably well within the range where we can talk about it being a rare event.